As you have learned in the previous part of this series of lessons on stalling, an unmodified swept wing will stall first near the tips. And since the tips are well aft of the centre of gravity, the loss of lift causes the nose to rise rapidly and further increase the angle of attack. This phenomenon of pitch up stalls more of the wing. Drag will increase rapidly, lift will reduce, and the aircraft will start to sink at a constant nose-high pitch attitude. This results in a rapid additional increase in angle of attack. Separated airflow from the stalled wing will immerse a high-set tailplane, or T-tail, in low-energy turbulent air, and elevator authority is greatly reduced, making it impossible for the pilot to reduce the angle of attack. The aircraft will become stabilized in what is known as the superstall, or deep stall. The two principal factors involved in the superstall are a swept-back wing and a high-mounted tailplane. But of the two, by far the more significant is the swept wing, with its tendency to stall at the tips, causing the pitch-up phenomenon. Aircraft such as the MD-80, Boeing 727, Fokker 28, and the BAC 111, the aircraft on which the phenomenon was discovered during its flight testing in 1963, all have swept wings and T-tails. They also have rear fuselage-mounted engines, which are the reason for the T-tail. But apart from the possibility of the engines causing some turbulence and blanking of the airflow once the aircraft is already stalled, they do not in themselves contribute to the stall. Several devices and design features that can delay the tip stall by various means were described in the last lesson. Methods of reducing the spanwise movement of the boundary layer include wing fences, vortilons, engine pylons, and sawtooth leading edges. Vortex generators are a frequently used design feature that not only delay tip stall, but also improve stalling characteristics by maintaining aileron effectiveness down to lower speeds. The wing root can be made to stall before the tips by changing the aerofoil section at the root, by fitting stall strips, or by fitting Kruger flaps on the inboard sections of the wing, alongside the more efficient variable camber leading edge flaps. Both of these types of flap are described in the lessons on high lift devices. An aircraft which exhibits, or is likely to exhibit, superstall characteristics must be fitted with a device that will prevent it from ever stalling. The device is the stick pusher, developed after the loss of the 111 previously mentioned. Once a superstall commences, its progression is too fast for human response, and the aircraft cannot be unstalled. The stick pusher is incorporated in the elevator control system, and, as its name implies, physically pushes the control column forward at a certain angle of attack before the critical angle, and reduces the angle before a stall can occur. The push force is typically about 80 pounds, which is regarded as being high enough to be effective, but not too high to hold in the event of a runaway. A cutout is included to dump the system in the event of a malfunction. But, once dumped, the system can't normally be reset in flight. In normal operation, once the stick pusher has operated, it will disengage automatically as the angle of attack reduces below a preset value.